So hello everyone, and in this video we are going to talk about something called a method of eigenvalue. Okay, so what is our question? The question is very simple. Consider this system, consider this linear system, right? Consider the linear system, x prime equals to ax. Clear? Now we want to solve this equation. Yes, given x0 equals to x0, we know that e power at times x0 is the solution. That we have already seen. Yeah, but that is fine. But in that case, you have to calculate exponential. Yes, and we have to know how to calculate exponential, which is, by the way, not a trivial task. Okay, so there is another way of computing this thing. That is actually, this is actually basically calculating the exponential only, but in a different context. Okay, so let me do this method of eigenvalue. So what we have is this. First of all, we start with this linear system x prime equals to ax. Yes, let us just try to solve it. Yes, without knowing anything, let's just try to solve it. See, if you have x prime equals to ax, let's say, yeah, one way of solving is directly, separating the variables and writing it like that. That you can of course do. But again, you can also try that, let's say e power some lambda, let's say t is a function which satisfies this equation, and then you can find lambda for which this holds. That also can be done, right? So and the similar thing, e power mx kind of thing also we do for second order equation. The same sort of idea, we'll try it here. Okay, now you see. But the thing is, if we just start using e power lambda t type of function, that won't work, because here the solution x of t is in Rn, right? Okay, so you have to multiply it by some vector v. Clear? Okay, so what we are going to do is this. Let x cap of t, I'm not writing x cap because x is, we understand that it's going to be a vector, right? So that is, let us assume that that is given by some vector v. Okay, so please remember v is a vector. That is why I want to write it. Okay, v is a vector. Let me put it this way: v times e power lambda t. Okay, so please understand v is a vector in Rn, and e power lambda t is basically a scalar. Where v cap, okay, is a arbitrary constant vector. Clear? Now you see, if this is a solution of this problem, then of course that solves 1, right? So if it solves 1, then therefore if we solve 1, what is x prime of t? It is nothing but lambda v e power lambda t, right? So it is nothing but lambda v e power lambda t, and that will be equals to what? A remains a, and x will be replaced by v e power lambda t. Okay, now if we put everything together, it becomes av minus lambda I, sorry, let me put it this way, a minus lambda I times v equals to 0, since e power lambda t is never going to be 0, right? Okay, so you see, what happened was this. Here, if you want x to be our solution, okay, so see, if x of t solves 1, okay, then lambda and v cap must satisfy, let's call it 2, satisfy 2. Okay, now you see, if lambda and v cap satisfies 2, okay, then of course lambda, so basically what is 2? 2 is nothing but the eigenvalue problem. See, the thing here is this: we are always assuming v to be non-zero, because you see, if v is 0, of course there is a solution, 0 solution. That's not interesting, right? So we are assuming v to be non-zero here. So basically we are looking for an eigenvalue problem. Clear? Okay, so if we can solve the eigenvalue problem, we get a lambda and a v, and you just put it there, and then you have your solution. Okay, so that's the idea essentially. Right, so let's look at this. See, the thing is, first of all, theorem. Let us write down a theorem then. Okay, so what is the theorem? Let A be a n cross n, okay, constant matrix, that is constant matrix. Of course, all of this is for the constant coefficient. Okay, constant matrix having n distinct eigenvalues, clear? Okay, now we know that if there are n distinct eigenvalues, there exist n linearly independent eigenvectors. This we know, independent eigenvectors. Yes, corresponding to each eigenvalues there are eigenvectors which are basically linearly independent, right? Eigenvectors which are given by v1, v2, vn, right? So since they are distinct eigenvalues, that is why the eigenvectors, corresponding eigenvectors, are independent. This we know from linear algebra. Okay, and so you see, for each eigenvalue lambda 1, you have a v1, right? So e power lambda 1 times t, v1, so times v1, basically times v1. So if you write it like this, you see this is a constant times a vector, right? So from the earlier calculation which you do it, this will actually solve 1, right? If lambda 1 and v1 is lambda is the eigenpair of A, then this will actually solve 1. So this is one solution which you are going to get, x1 of t. And similarly, for every I, xi of t is going to be this solution. Okay, and since it is a n cross n system, so A is a n cross n system. Let's just write it as n cross n system. A is a n cross n system. Okay, so since this is a n cross n system, what happens is we know that the solution space is of dimension n. So there should be n linearly independent eigenvectors, right? Linearly independent solutions, right? So what we can say is this, then the general solution of 1 is given by x of t. Clear? So this is general solution. Let me put it this way, xg, that is the general solution. This is given by c1 times v1 e power lambda 1 t, okay, plus c2 times v2 e power lambda 2 t, plus cn times vn e power lambda n t. Clear? Now you see, if initial data is given, then you can actually precisely calculate what c1, c2, cn are. So basically you can calculate the c, yes, and then your solution is also going to be a unique solution. So you can actually compare this thing with the fundamental matrix and the matrix exponential. Here, okay, so see, the thing is, hence we can write it as this, xg of t, let's write it as this, can be written as phi of t, the fundamental matrix, times a constant c, constant matrix, n cross 1 matrix. Clear? Okay, so this is a constant matrix, right? We know that this is true. We have looked at it previously, so we know that this is true. And so what is the fundamental matrix set? So this is the fundamental matrix, right? Fundamental matrix. Okay, so what is the fundamental matrix here? Where the fundamental matrix phi of t, okay, so this is a method of actually finding fundamental matrix when it has n distinct eigenvalues. You see, the first row will be v1 times e power lambda 1 of t, the second row will be v2 times e power lambda 2 of t, and it goes on like this. The nth row will be vn times e power lambda n of t. Clear? So that's your fundamental solution, and you can also write the solution in terms of this. So it's not a problem, anything is fine. Okay, so let us start with an example first. Yes. So let's say we want to solve this problem. X prime equals to 2, 1, 1. Yes. 1, 2, 0 and 0, 0, 2. Okay. Find the general solution essentially. Times x. So find the general solution. So what do you mean by general solution? All possible solutions. Clear? Okay. So now you see, first of all, as we have seen that this problem, first of all you have to find the eigenvalues. So the eigenvalues are given by given by 1, 2 and 3 and 3. Clear? Okay, so you have to check this part please, and this is very easy to do that, right? So we can do it. And the corresponding eigenvectors, okay, the corresponding eigenvectors are corresponding to 1, we have 1, minus 1, 0. Clear? Corresponding to 2, we have 0, 1, minus 1, and corresponding to 3, it is basically 1, 1, 0. Clear? So this is lambda equals to 1, lambda equals to 2, corresponding to lambda equals to 2, and corresponding to lambda equals to 3. Okay, so please don't change the order, because otherwise they won't be a solution. Okay, corresponding to lambda, let's say j, if Vj is the eigenvector, then Vj e power lambda j t times Vj will be a solution. Okay, so you can't change the orders, so you have to be very careful about it, right? So therefore, what is the distinct eigenvalues? So the eigenvectors are linearly independent, right? So the general solution in this case, the solution space is of 3 dimensions. So the general solution x of t will look like c1 times, okay, the vector 1, minus 1, 0 times e to the power t, plus c2 times the second vector 0, 1, minus 1 times e to the power 2t, plus the third vector c3 times 1, 1, 0 times e to the power 3t. Yeah, that's what you are going to get. Now, what the one last line, you should write it like this. Okay, so it should look like this. It is, so maybe I can write it here. Yes, it should look like c1 times e to the power t plus c3 times e to the power 3t. Write it properly. See, x of t is in R3, right? Okay, so x of t is nothing but x1 of t. Okay, you don't have to write this part. This is just for your information. x2 of t, x3 of t, right? Okay, so x1 of t is this, x2 of t is c1 times e to the power minus c1 times e to the power t, right? Plus c2 times e to the power 2t plus c3 times e to the power 3t. Clear? And similarly, the third expression is c2 times minus c2 times e to the power 2t. Yes, that's what we have. So this is the general solution, right? You can also write it in terms of a fundamental matrix. Okay, so what is the fundamental matrix? So in terms of fundamental matrix, if you just want to find out the fundamental matrix, therefore the fundamental matrix looks like this: e to the power t, e to the minus e to the power t, and 0, right? Similarly, the second part is 0, e to the power 2t minus e to the power 2t, and the third part is e to the power 3t, e to the power 3t, and it is 0. So that's your fundamental matrix. Clear? So this also shows you how to find fundamental matrix, at least in the case when there is like distinct eigenvectors. Okay, sorry, eigenvalues. Okay, so now let's look at if the eigenvalues are complex. Okay, what happens so if the eigenvalues are complex? So case 2, let's call it case 2, complex eigenvalues. Complex eigenvalues. Okay, so what happens in, see, the thing is in this case, if you have to remember this thing, if alpha plus I beta is an eigenvalue, so please remember this, given n cross n matrix A, okay, if alpha plus I beta, okay, beta not equals to 0, that is an eigenvalue, that will imply alpha minus I beta will also be an eigenvalue. So conjugate will be there, right? So that this part we already know. Okay, right. So now what happens is this. So basically with this, what we are going to do is, again we are going to do exactly the same sort of thing. So we start with finding a e power lambda t kind of thing. Okay, right. So you see what we are doing is this. Suppose so alpha plus I beta is a eigenvalue is given, and let's say that, okay, so let alpha plus I beta is an eigenvalue and the corresponding eigenvector, and v, let's call it this vector as v, is an eigenvector corresponding eigenvector. Okay, is an eigenvector corresponding to alpha plus I beta. Clear? Okay. So what does that imply? That v bar, okay, will be the eigenvector, okay, corresponding to alpha minus I beta, right? So this is just your basic linear algebra. If you do not know this thing, please go and do this part again, right? Okay, so what I am trying to say is this: if alpha plus I beta v is that if that is a eigenpair, right, then alpha minus I beta v bar will also be an eigenpair. Okay, so that is always there, we already know this part. Okay, right. Now you see that choose x1, yeah, this is a new function x1, okay, to be v, the vector v, okay, times e power alpha plus I beta times t. Just like the previous case, we are just doing it, but here we are doing it for a complex one. Okay, it's just that a little bit complicated. So basically the solution is a complex valued solution. Okay, so we are just assuming here it is a complex valued solution. Clear? Okay, now if this is the case, then you see that if you have so choose this such that x1 satisfies the equation, right? Satisfies x prime equals to ax, okay, n cross n. Please remember, a is a real, n cross n constant vector. Okay, right. So a is a real vector, yes, but the solution which you are going to get here, in this case x1 of t, we are choosing it such a way, we are saying that let the complex valued function. So here I should not write it as a solution, I should write it as a function. So let this complex valued function solves the system x prime equals to ax. That's what we are assuming. Clear? Okay. So now, so x2 of t, if we define x2 of t, okay, let us put it this way. Okay. So hence x1 of t is v1 e power alpha t cosine beta t plus I sine beta t. Okay, this is true. Okay, so if this is the case, so you see it becomes essentially v1 times e power alpha t cosine beta t plus I v2 e to the power alpha t sine beta t. We can write it like this. So basically we can just break up the real and the imaginary part. Okay, right. Now you see that you can easily check this part. Check that v1 times e power. So please remember this v. Sorry, what is v1? Okay, let's just call it v1. Let's just call it v1. Okay, v1. Now you see v1 times e power alpha t cosine beta t and v2 e to the power alpha t sine beta t solves x prime equals to ax. Okay, you remember this sort of thing we did earlier also. So basically, if there is like a plus ib solves a function at plus ibt solves the linear equation x prime equals to ax, then at and bt individually solves the equation. Okay, so they are real valued functions and they solve the equation. Okay, solve this and are linearly independent. Okay, I hope this is not a very difficult thing for you to check. Okay, so please check this part. I made some mistakes here. This let me put it this way. This v1 bar, v1 bar, not v2, v1 bar. Okay, clear? Okay, and again here also it should be v1 bar. Okay, the vector, right? So you have to check this part. This is not very difficult to see. You can easily check this part. Clear? So please do that. Okay, so now you see the thing is we can, I mean, once you check this part, we have this theorem. Then theorem, okay, that let A be a n cross n constant matrix, n cross n real valued constant matrix. What is real valued constant? Basically, let's just say it is constant matrix. Okay, constant matrix, real constant matrix essentially. Let me put it real constant matrix. Real constant matrix. Okay, and if A has a complex eigenvalue alpha plus I beta, that is beta not equals to 0. Okay, so complex eigenvalue. Okay, and V bar is the corresponding eigenvector. Yeah, if this is true, yeah, then x prime equals to ax has two linearly independent solution, okay, real valued solution. This is important, real valued solutions. And what are they? They are given by let's just write it x1 of t, which is, you see, v1 e power alpha t cosine beta t, so which is nothing but the real part of x1. Okay, so which is given by the first one is, let's just call it y1, which is real part of x1. Okay, and also y2, which is nothing but the imaginary part of x1. Clear? Okay, real part of x1 and imaginary part of x1, so which is basically this and this. Okay, so they individually are two, I mean, linearly independent solutions, right? Okay, so this is one of the way which we can work out this problem. Okay, so now what we are going to do is essentially, maybe we can look at example of how to solve. Oh, 1 second, I think it is okay. Yeah, this is fine. Okay, right. So now what we are going to do is maybe work out this problem. So for example, let's do a small example here. Okay, so in this example we are going to look at a 2x2 system. Yes, 2x2 system. We will do it for a 3x3 system also. All of those examples we will do it, but for now 2x2 system. So let's say I have this matrix x prime equals to 2 1 0 2 times x. Okay, and I want to find out the eigenvalues. Okay, I want to find out the eigenvalues. So in this case it is 2 2, right? Should it be okay? This should not be. This doesn't have any complex eigenvalue. Let me change it to a complex eigenvalue. Maybe 1 1 and okay, minus 1 1 1. Let me do it this way. Okay, so it will have complex eigenvalue. So what is the complex eigenvalue? 1 plus minus I. Okay, so the system has complex eigenvalue given by x of t, which is nothing but given by 1 plus minus I. Clear? They comes in conjugate, right? Okay, now the eigenvectors we have to find out. Okay, so for 1 plus I, if you want to find out the eigenvectors, yeah, okay, so please check this part, check this part. I am not 100% sure about this calculation. I think it is okay. Okay, so as far as I can calculate, a lambda av equals to lambda v, right? So if you calculate it, it should look like minus minus y. Okay, so check minus I and 1, and another one for 1 minus I, it should be I1, right? One second, for 1 plus I, it should be, yeah, so this is corresponding to lambda equals to 1 plus I, and corresponding to lambda 1 minus I, it should be this sign should change. So this is 1, it's corresponding to 1 minus I. Okay, so please check this part. I'm not 100% sure it should be the case. Okay, but anyway, you do understand the concept, right? You please do this part yourself. Are the corresponding eigenvectors. Okay, so once you have this, then what are the solutions? So basically, you see what is y1 of t. Y1 of t is nothing but you see e power 1 plus I of t, right, times minus 1 I, right, and y2 of t is nothing but again e power 1 minus I of t, and then corresponding to 1 minus I, it is y, right? So I and 1. Clear? Okay, so this is there. Now you see the thing is these are complex values, right? So I have to make it real value. Doesn't really matter y1 and y2. You do not have to write it like this. Okay, but anyways, so fine. So if you write it that or like this also, then also therefore the general solution is the real part of this and the imaginary part of the individually. So you can take y1 or y2, doesn't really matter. Okay, so you can take the real part of y1 and the imaginary part of y1, or real part of y2 or imaginary part of y2, both will work. It's exactly the same thing. Okay, with some constant basically. Okay, so how do you write down the the general solution? So therefore the general solution will be given by I should break it up, right? I should break it up. So it is, so let's do it here. You see y1 of t is nothing but e to the power t, e to the power I t, and then minus I1. Okay, so it is e to the power t cosine t plus I sine t. Clear? And then minus I and 1. Okay, so it is e to the power t cosine t minus I1 plus I sine t e to the power t minus I and 1. Yeah, this is what we are going to get. Okay, so if you calculate this part, see, if you calculate this part, it becomes I e to the power t cosine t plus e to the power t sine t. Okay, and similarly e to the power t cosine t minus I e to the power t sine t. Okay, I hope the calculation is fine. Yes, please check this part. So I hope this is fine. So now basically the real part of y1 and the imaginary part of y1 you just separate it out. So general solution will look like this: c1 times e to the power t sine t and cosine t. Okay, so you see this part and this part, right? That's the real part, and the imaginary part is this one and this one. Okay, plus c2 times e to the power t cosine t and minus sine t. Okay, c1 c2 is in R. So that's your general solution. I hope this is fine. Okay, sine t cosine t minus sine t. Clear? Okay, so so this is how you solve the problems. Okay, and if I ask you to find the fundamental solution, so there is a please there's this check part, so please check this. Find the fundamental matrix of A. What is A? Matrix corresponding to this equation A, which is 1 1 minus 1 1 corresponding to this matrix. So I'm not writing this. So you find the fundamental matrix for this system. Okay, so that's there, right? I hope this is fine. Okay, now the thing is this: we have to see the third case. What is the third case? The distinct case, case 3. Okay, what is case 3? Case 3 is multiple eigenvalues, actually repeated eigenvalues. Okay, repeated eigenvalues. Okay, so how do you find repeated eigenvalues? Okay, so now let's say that let A be a n cross n constant matrix, of course, constant real matrix. Okay, now the thing is with eigenvalues. What are the eigenvalues here? Lambda 1, lambda 2, lambda n. Okay, the important thing is this: these are not necessarily distinct. So basically they may be, they may all be same, or at least 2 or 3 of them they may be same. So basically they are not distinct, that's all. Okay, they are not necessarily distinct. Okay, and let there are n distinct eigenvalues, sorry, what am I saying? Not distinct, n linearly independent. Okay, I should write it this way: linearly independent eigenvectors given by v1, v2, vn. Clear? Then the general solution, I think you have already guessed it. What is the general solution? X of t is nothing but c1 times v1 e to the power lambda 1 of t. Exactly the same. Yes, c2 times v2 e to the power lambda 2 of t. Why is it the case? Can you think of any case? Maybe what you can do is pause this video and think of why this is happening, why this should be the case. See, what is happening is this: even though lambda 1, lambda 2, lambda 3 are not distinct, okay, the eigenvectors which you are going to get, they are linearly independent. That is given. Let's just assume that that is true. That may not be true, right? If that is true, then so v1 times e power lambda 1 t, v2 times e power lambda 2 t, vn times e power lambda n t, this set of matrix, this is linearly independent, right? Okay, they are linearly independent, and if they are linearly independent, then they actually form n-dimensional basis for the solution space, and then the general solution is this. Yeah. So in this case, it's very easy and it's not a problem. The problem lies here: if there is a not n linearly independent eigenvectors. Okay, so the problem is this: defective eigenvalue. Okay, what do I mean by defective eigenvalue? So let's say that if a n cross n matrix clear has less than n linearly independent eigenvector. Oh, sorry, eigenvector n linearly independent eigenvector. Okay, yeah, okay. Then A is called deficient. Deficient means it's not enough. There are not enough linearly independent eigenvector. Okay, so basically the algebraic multiplicity is more than the geometric multiplicity. That is what